Hello, this is Daniel Oshro. I'm completing the exam for Chapter 25. My life path number is number 1, so that's the problem number I'll be completing. So for the first part here, Part A, you are presented with several long cylinders made of different materials. Which of them are likely to be good conductors of electric current? In the textbook, conductors are described. Let me see here. In an ordinary metal such as copper or aluminum, some of the electrons are free to move within the conducting material. So metals are materials that have free electrons, higher concentrations of free electrons. So metals are going to make for our best conductors. So therefore I selected copper, aluminum, and gold because those are the only metals in this list. So that's part A. Part B, metals are good conductors of electric current for which of the following reasons? Like I just stated definitionally, the conductor, a conductor uses free electrons which create a drift. How do we say it here? A drift velocity. So the more free electrons something has, the more it will allow them to move and conduct the charge coming through it. So they possess high concentrations of free electrons. Again, definitionally for this question, which of the following is most likely drift speed of the electrons in a copper wire? We have down here, while the random motion of the electrons has a very fast average speed of about 10 to the 6 milliseconds, the drift speed is very slow, often of the order 10 to the negative 4 meters per second. So that's our answer. All right, part D. So this one we can have a little fun with. All right. So it gives us radius and drift speed for each wire, and has this list which is going to have the most current to least current. So basically, we have a formula over here. I equals N Q V A. So N is going to be our concentration of moving charged particles, so like how the amount of free electrons we have. Q is going to be our charge per particle. V is going to be our drift speed. A is going to be cross-sectional area. And for a wire, which we're going to say is a cylinder, the area from any one section of it is just going to be the area of a circle, which is pi r squared. So considering everything else would be constant with these values they give us, we're just going to go I equals V pi r squared. So for the first one here, we have R equals 2R, and V, our drift speed, equals 2.5 V. So I1 is going to equal it's going to be 2.5 V times 4R squared equals 10R squared V. For number 2, it's going to be R equals 3R, V equals 1V. So we're going to have 1V times 9R squared, equals 9R squared V. For I3, we're going to have R equals 4R, V equals 0.5 V. So we'll have 0.5 V times 16R squared. And that's going to give us, we'll just throw pi in here, but again, they all have pi, so it really doesn't make a difference in terms of ranking them. So it's going to be 8R squared V, and then I4 is going to be R equals 1R V equals 5V. So 5V, and then just going to be R squared equals 5R squared V. So that is the order I have them in here. And then part of the drift speed of the electrons in a wire depends strongly on which of the following factors. So again, definitionally here we have drift speed. Okay, so the net effect of the electric field E is that in addition to the random motion of the charged particles within the conductor, there is also a very slow net motion or drift of the moving charged particles as a group in the direction of the electric force. F equals Q, which is your charge, times E, which is the electric field. This motion is described in terms of drift velocity of the particles. So, that being stated, we have our choices: cross-sectional area of the wire, mass of the wire, and temperature of the wire. None of that is in our formula for drift speed, or for force, which is related to drift speed. However, electric field is. Therefore, I chose the electric field in the wire, and that's all.